Okay, the next topic that we're going to look at is something called electromagnetic induction. Now, that may sound a little bit scary, but it's a very basic idea. Here's the basic rule. I've got a loop of wire, and it could be several loops like I've got here in this figure. It could be a single loop, but these wires are connected to some kind of meter. So this meter is going to be something that detects the presence of current. And then I'm going to take a magnet. Now, if I'm just holding the magnet here, nothing's going to happen. But if I pull the magnet out, or if I push the magnet in, what's going to happen is that's going to create current traveling through the wires. And so, actually, it's kind of interesting. If I push it in, I'll see the needle on my current meter deflect in the positive direction. And if I pull it out, I'll see the needle deflect in the negative direction. So what that means is that if I push it in, the current goes one way, and if I pull it out, the current goes the other way. So the current can either go that way or the other way, depending on whether I'm pushing it in or pulling it out. And this is the basic idea of what we call alternating current. If I take this magnet and I just keep shoving it in and out, back and forth, the needle's going to go positive current, which means the current's going in one direction, back to zero, the negative current, meaning the current's going in the other direction. The current is going to be going back and forth through the wire. So the current goes this way, the current goes that way, and then over and over, as I push this guy in and out, I get alternating current. Now, another way that you can get alternating current is to have a fixed magnetic field. So for example, here I've got a bar magnet with a couple of bar magnets with their north and south poles. So I'm going to get magnetic fields going between them. And if I have a coil in here and I rotate the coil, I spin the coil around, that's going to create the same effect of pushing the magnet into the station. So let me say this again so that it's really clear. Over on the left here, I've got a stationary coil and a moving magnet, and I'm shoving the magnet into the coil. Over here, I have stationary magnets and a coil that can rotate. And so what I'm doing in each of these cases, I'm changing the magnetic fields going through the coils. And by changing the magnetic fields, I create electric fields which will drive currents down these wires. Remember, electric fields push charges. And so simply by shoving the magnet in and out of this coil, I can generate alternating current electricity. Simply by having a fixed magnet and rotating a coil in it, I can generate alternating current electricity. This process is called electromagnetic induction. And it's basically a way of being able to do physical work, like pushing a magnet into a coil, and converting that work into electrical energy, in this case, the energy of an electric current. So the next thing we want to look at is Faraday's law. And Faraday's law tells us that if I've got a loop, now keep in mind these loops need to be conductors. If the charges can't flow down the wire, none of this is going to happen. And so I've got a loop, and I could have something with multiple loops in it. It doesn't matter. So I can have a single loop, or I can have multiple loops. And let's say I've got a bar magnet with a north and a south pole, and I shove it into the loop. And I can shove it over into this group of loops over here. It doesn't matter. There's going to be a current that's induced in this loop, and it's going to be driven by a voltage. And the voltage is what actually is going on. The changing magnetic field seen by this loop. So as I push this magnet closer to the loop or push it through the loop, the magnetic field over here gets stronger. And so the loop is seeing a change in the magnetic field at its location in space. And so that's going to induce a voltage. Now, the induced amount of voltage in that loop, and remember that induced voltage is going to make a current go around that current carrying loop. That induced voltage is equal to the number of the loops. So over here I'd have one loop, over here I'd have three loops or whatever. And so that's what the number of loops is. And then the change in magnetic field with time. In other words, how strong the magnetic field becomes or how weak it gets if I pull it in the other direction. The strength of the magnetic field is changing with time, And if I can measure that or figure out what it is, that is what gets multiplied by the number of loops to tell you how much voltage gets induced. And again, that's called Faraday's law. Here you can see another image showing the kind of principle that I was talking about. I've got a wire here, and I've got a meter that will detect the presence of current. If I shove a magnet over the wire, then I'm going to get a pulse of current. And of course, if I pull the magnet up, I'm going to get the current in the other direction. It'll work the same if I make the magnet be fixed and I grab the wire and I shake the wire up and down. Again, that needle will go back and forth. I'm generating alternating current. Now, here's a checkpoint of our understanding. If you push a magnet into a coil, as shown in the figure here, figure 9.25, you'll feel a resistance to your push. Why is the resistance greater in a coil with more loops? Well, it turns out that the more loops you have here, the more current you make. And so it takes more energy to make more current, so you have to push harder. And you'll actually feel a resistance against pushing this magnet into this loop of coil. So why is it that we get more current with more loops? Well, that's just what we were talking about on the previous slide. That's Faraday's law. The amount of voltage induced depends on how many loops you have. So more loops means a bigger voltage, and that means more current. But the energy to drive that current has to come from somewhere, and it's coming from you actually doing work, force times distance, to push that magnet into the coil. And in order to make more current, you have to do more work. In other words, the distance is going to be the same, but you're going to have to push harder to get that coil, to get that magnet inside that coil. Now, I said that if you have a loop that's turning in a permanent magnet, you can generate an electrical current. And this is sort of a schematic showing how this can be. So here I've got this fixed magnet, I've got a magnetic field going from one pole to the next pole, and I've got this loop in here that's attached to a crank. And so as this guy here grabs this handle and turns this crank, he's rotating the loop in the magnetic field. And so the magnetic field lines passing through the loop is seeing a changing magnetic field. That means whenever you have a changing magnetic field and a loop, the changing magnetic field through the loop is going to generate a current in that loop. And of course, as we've already talked about, that's going to be an alternating current. So the current's going to go one way, and then it'll go the other way, back and forth. So it'll go into the light bulb, through the light bulb, it'll make light, it'll come out the light bulb, and then it'll reverse and go the other way, just back and forth, over and over. That's alternating current. Now we want to talk about alternating current. Again, we said what that means is the current first goes one way, and then it stops momentarily, then it reverses direction. And so if we think of the reverse direction as being in the negative, we can actually plot the voltage and the current. The two graphs would look very similar to one another, but here's a graph of the voltage, and so we can say that when the loop is in this position, the voltage is high, and then as you go down, when the loop is flat, you've got no voltage, but as you flip it the other side, you have a reversal, and the current's flowing the other way, and the voltage driving that current is negative, and it just keeps repeating as the loop spins and spins and spins. You get a voltage that is constantly alternating back and forth, and that's going to create a current which is constantly alternating back and forth. That's why we call it alternating current.